Okay, I'm going to be speaking about the world's first certified passwordless car dealership. Right off the bat, I can say this is not the most cost-effective passwordless project that's been done. It is the first of many lessons learned throughout the project. Unfortunately, I have limited time, so there's a plethora of stuff I could go through, but I've limited it to about 3 or 4 key topics, probably some of the most interesting stuff. There may be questions that arise about other aspects, which I'm happy to take during the Q&A. You'll note, interestingly, I'll be actually speaking very little about the building envelope. There are some interesting aspects, some I'll talk about, but most of it will be focused on other aspects. So just a bit of background on the project. It is a car dealership. It also has an integrated repair shop. It is in Red Deer, Alberta in Canada. That is nestled between Calgary and Edmonton for those who are more geographically inclined about Canada. And it has a substantially cold design temperature of minus 29 C or 20 Fahrenheit, which really put us to the test in terms of finding solutions that could work in this environment and still meet various requirements. Just a highlight of some of the key elements, if you will, of the project. There were strict corporate guidelines. I don't know if anyone's actually worked on a regular car dealership, but they dictate very much what is required, and you can't veer from them. It is an unforgiving climate, being such a cold climate. There is a dearth of products that are suitable for use in cold climates, and so that was an interesting thing to navigate. We unfortunately had a constrained consulting budget, which showed up, unfortunately, because we didn't have as much space or time to really investigate some of these issues. And so certainly some of the solutions that we came up with were suboptimal. Interesting note of the project as well, although I won't really be speaking about this, is it is a timber construction, which is, I would argue, it's probably highly unusual for a car dealership. I can't say it's never been done, but it's usually steel construction. So that's a neat note on that. Okay, and just a statement from the owner. It is actually a family-owned business, been run for 50 years. They have a few car dealerships, and he's not an environmentalist himself, but he did see, there's good alignment with Passivos in terms of the long-term value. And he found as well, it's just thinking more broadly, that it would be an important statement for both the industry as well as the country. So it was great to be able to get him on board in doing this project. Just some scenes, trying to, again, limit what I show in this 15 minutes. So typical, basically it looks like a typical car dealership. You can't tell it's Passivos from the outside or inside. Yeah, so I mean, there's the showroom, pretty typical reception area. I don't have any photos, unfortunately, of the office space. There's a bunch of sales offices as well as back office support. It is 2-level building. This is the drop zone, basically our drop-off car area, basically for showing the customers cars. Customers can drop off cars as well, and they'll bring them in this area sort of before they get into the repair shop. And then we have the repair shop itself. Again, pretty standard layout. And I think an important thing about this project is service to the client is of the utmost importance, both customer service as well as the repair shop operation. And so nothing could disrupt that. And so anything that Passivos required that may conflict or work at odds against it, we had to navigate that to make sure service wasn't actually interrupted. Okay, so the first thing I'll talk about in terms of challenges was the west-facing showroom. Because of corporate requirements, all the showroom glazing or the main facade had to face west, and it had to have a lot of glazing. And there's no way around this. We couldn't put overhangs on. Well, I mean that now naturally has less of an impact in the west, although it still has some. But again, corporate guidelines meant we couldn't do that. So we really had to look at various options. One thing to note about Red Deer and this area of the country in general, it's the sunniest area in Canada. It's actually got 50% more west radiation than Germany. So we're dealing with, although it's cold, it's sunny. So we actually have a lot of solar gains to deal with. There is a low amount of natural shading. It's a very flat area, and not many trees or any no big buildings of note. We did investigate actually planting some trees, but that actually, unfortunately, we couldn't find a good balance between allowing the sun in winter and blocking it out in summer. Just the design limits on this project were very tight, and we couldn't actually make trees work on the project. We looked at external blinds, which is a common solution for passivhaus projects. They wouldn't work for a variety of reasons. This is a fairly windy area of the country. And so there's that risk of damage, very gusty as well. You can see it's almost a two-story facade, so having external blinds drop down that far would be a bit of a feat. And aesthetically, the client didn't really want that on the outside. So that solution was abandoned as well. We looked at electrochromic glazing, but we found that was too expensive, as well as we couldn't actually find glazing that met our specification requirements, as in it could block out enough sun in the summer and reduce enough heat loss in the winter as well. I think the glazing, it's still relatively new product, I suppose, on the market, and just doesn't have the same range of specifications as you see in standard insulated glazing. So what we ended up doing, which we're not the most pleased with, but given the constraints, this is what we could do, was they did accept to have insulated spano-pandrel at the top, so we did get much more highly insulated area for that section of glazing. And then we relied on operable internal blinds with the manual overrides that they can control it for customer experience. Not ideal at all, but it's what we could manage on the project, unfortunately. And we did a bunch of analysis on this. We I don't really have so much time to speak about, but maybe in the Q&A that may come up. But we basically had to deal with the additional peak cooling load that this entailed with all this extra west or remaining west glazing. Overhead doors, here's another envelope area which we've honed in on. And the first thing we really looked at was the design itself. So when we first got the floor plans, we saw 7 overhead doors on the plans. Now a normal project would just go ahead and say, okay, well, we need 7 doors. Okay, which ones are we going to choose? And we'll install them. And we always take an approach of, well, what are we looking at? What are we actually trying to achieve? And can we do it maybe in a more energy efficient way that doesn't necessarily need as many components? And so we actually proposed a design to the architect and the client that could reduce the number of doors down to 2. And so any impacts that these overhead doors would have would be not fully mitigated, but substantially reduced. Unfortunately, the client said that would affect service too much, and so we ended up compromising on 4. So we almost cut them in half, which is important for the performance as well as the cost, because these things are not cheap. Okay, and that's, I think, a key, and I mean, I see this on numerous projects. I think, passivhaus of really rethinking how we do things, right? It's asking those questions which aren't normally asked on projects. Well, do we need this many doors, as a simple example? So in terms of the doors themselves, we looked at, okay, what impact is this going to have? We looked at some studies and calculations done for person doors in, I think it was in Germany, to try and get an assessment of how much heat loss would be. So we used that to help inform calculations for this project. We ended up calculating about 9 CFM per door opening. Is that actually the case? We'd have to really measure it. So it's not, not confirmed. They are fast acting doors, so they go up and down quickly. So there wouldn't be that substantive amount of loss, provided they're closed readily after the car enters. But we don't know this for certain. But with a bit of sensitivity analysis, we reasoned that actually this isn't going to have a big impact on the heat loss overall. As long as it's operated fine, then actually we don't need to concern ourselves much about that. The greater concern turned out to be a standby air leakage. And so this, you can see here about 70% of the, if we can see these doors as part of transparent envelope, even though they don't really have glazing in them, or about 4% of the wall area. But the potential impact on the overall building air tightness could be substantial. And unfortunately, conventional overhead doors have almost no regard for air tightness. And so we said, okay, well, how do we actually come up with some estimation of what we're going to lose through these doors without actually having them installed and tested, and with the risk of not actually having the doors perform? So first off, we set the actual air tightness target at 0.4 ACH at 50 pascals, because there was actually a, just in terms of trying to meet the space heating demand, we needed to push the air tightness to that level. So that was actually our design target, not just, what came out of the testing. And then in terms of assessing the air tightness, we couldn't find anything in North America. So we referred to the European rating system for overhead doors. And we deemed that, well, there were different classifications. We could only locate a manufacturer that would produce a class 3 door, which actually would increase the air tightness, the overall air tightness, by 10%. So you can see the sensitivity here of these doors, just 4 doors in the building. But the nice thing is we installed them and we ended up getting a 0.4 on the test. So just snuck into our design requirement. However, we, in the end, as we went through the design, we technically could have relaxed the air tightness just because of some changes and improvements into other areas of the design. And so we could have gotten away with a 0.6, but we didn't tell the construction crew that. So the target still remained 0.4, and they achieved it. Internal heat gains, another key element. We're dealing with processes that we've not dealt with before. So what was important and what we set out to do early on, because we knew this could have a big impact on the energy performance of the building, was to try and estimate how is the equipment going to be used, and subsequently how many internal heat gains would be produced from that. And so this was, luckily, we were dealing with a client who had they're operating already a few other car dealerships, so they could at least tell us what they would expect to be installing in terms of capacity of the equipment. And then they could give us a rough idea of, how much time that a particular equipment could be or would be operated. Now, we couldn't say, is that 10 minutes per hour at peak or at an average power. We don't know what the average power is. And again, budget constraints, so we couldn't go on and start doing, monitoring of the other car dealerships, unfortunately, and they're not even metered to be able to derive that data. So it was basically our best engineering estimate of what the internal heat gains were. So you can see in the repair shop, they take up, from our estimate, about just over half of the internal heat gains. Another aspect of the heat flows or energy flows was the temperature difference. So showroom at 20 degrees or 68 Fahrenheit versus the drop-off area in the repair shop at a bit lower temperature. So you do have to account for heat flow between the zones in the energy modeling. And then one thing which we didn't think about at the beginning, and luckily we did partway through the design, was actually we're bringing these cars into and out of the shop, and you know, they could come in very hot. You know, customers driven for half an hour, drop the car off, and now it's going right into the repair shop. And you know, this is up to about 600, 650 Fahrenheit, so very hot engine. Or they could be coming in as ice blocks because the customer could drop off their car. You know, it's minus 20 degrees outside, say Celsius, and it's sat overnight. And so they're bringing this car in an ice block. And so based on, you know, rough estimates of how much heat these cars could contain, as well as how the customers interact and how the dealership deals with the cars, we did some calculations and found that roughly speaking, the actually energy flows of heat gains and sinks balanced out. Ultimately, again, this is a sort of an estimate. You know, we'd have to do some detailed monitoring, really, or whatever, to figure out how accurate this is. But you know, it's our best estimate. And then we also have the cars running during repairs. So most cars, depending on the type of repair, they'll likely be run for, say, 5 minutes, 10 minutes, or whatever, just to test various things. And so that was about 14% of the internal heat gains. However, that's naturally quite sensitive to the runtime of the car. So again, best estimates. Okay, when we look at our ventilation system, car exhaust, so repair shops, obviously if you're running a car, you're going to be pumping out car exhaust. You don't want that to go straight into the building. So you need to separately exhaust that. And there are 6 bays in the building. Each bay requires 400 CFM. And we thought at first, well, can we not just connect them? Because they're connected straight to the tailpipe, right? So can we not, then if we need the exhaust at the tailpipe, can we not just take makeup air and stick it right into the intake, or as close as we can into the intake of the car? But the client was like, no, that will disrupt the service. We don't want something we have to clip to the car. That's just, yeah, it doesn't work. So we couldn't kind of, I don't know if that's a cheat, but we couldn't actually just direct the cold air into the car. So we had to deal with this load, and it turned out to be quite a huge ventilation load because there's 400 CFM times 6, so 2400 CFM total. For reference, the whole building background ventilation rate for the showroom, drop zone, and this repair shop was 740. So you know, several times higher. Now, naturally, this isn't run the whole time, but it's quite a bit of air. So we were able, I mean, the standard solution is just to tie all these hoses to one fan and blow the fan. So whenever a car is run, that one fan blows, but then all 6 bays evacuate, right? And if there's only one car running, you don't actually need that. And so again, this whole thing of like, well, what's required? How can we meet the functional requirements while still reducing energy, the energy demand? And so we managed to convince the engineer to say, okay, well, let's put separate fans on, one on each hose, that only each bay runs when the car located in that bay is actually running. And now, unfortunately, somehow there was miscommunication and drawing issues. So 6 fans didn't get installed, only 2 fans got installed. And luckily we had a bit of buffer because we met that 0.4 air tightness target, and we could get away with 0.6. So we were able to accommodate that oversight. Now we did actually look for heat recovery options. But whereas with kitchen exhaust, although it can be expensive and sometimes complicated and maintenance, you know, high maintenance, you can find solutions. Here, no matter what solution we look for, basically it wouldn't work. None of the manufacturers were warranty their equipment for car exhaust. So we just, there was nothing we could do that would exchange heat between the exhaust and the makeup. We did consider an earth tube or a ground loop, like a glycol brine loop, to preheat the air. However, this is a huge capacity. I mean, compared to the background ventilation, that would be a large tube or ground loop. And the average temperature, ground temperature in the winter in Red Deer's 4 degrees or 39 Fahrenheit. So we're not actually going to be extracting a lot of heat. So big expense, not a big temperature uplift. And it wasn't feasible. And yeah, I think that's those are the key elements. I don't know how I'm doing for timing, but basically, yeah, I just want to key things about cold climates in general was keeping the things as simple as possible, reducing as much whether it's like overhead doors or systems or whatnot like that. That's critical. For cost effectiveness. We had some issues with the mechanical engineers in terms of exploring options. So we really look to work with open-minded mechanical engineers. They are out there. We don't always get them on projects. We definitely need cold climate innovation. There's some other elements like windows and stuff we didn't touch on, but we definitely need some there. Think through the details early. That's a pretty common thing in general for passivos. Estimating the equipment and occupant loads is crucial early on. Identifying all the energy flows. We missed some at the beginning. It's a new type of building. So just watch out for that, and add some buffer. Luckily, we did add a bit of buffer into it, and construction changes, things like that, allowed us to account for that and still manage to certify as well. So, and yeah, if you'd like a challenge, then design a passivhaus car dealership in a cold climate. So yeah, that's basically it. Again.